Hello. In this video, we're going to continue our introduction to classes and objects, and we're going to look specifically at methods, or behaviors of objects. There are two types of methods to consider: instance methods that require a specified object to execute, and class or static methods that do not require a specified object to execute. We're interested in instance methods in this case. We'll look at the other type in a later presentation. So if you look at this code segment here, we see that we create two fraction objects, we populate them with some values, and then we have this line down here called g.reduce. Reduce is an instance method associated with the fraction class. How do I know this? I know this because it's being invoked with an implied object. G is the object that is calling the reduce method. This means that G is the object that will be changed once that method is done executing. Very important, instance methods require an implied object, because an instance method might change fields and it needs to know who it's changing. So if I invoked reduce, who is being reduced? The implied object is. So instance methods don't have static in the method header. An instance method must be called with an implied object. To access the implied object reference, we use the keyword this, and we'll see an example shortly about this. Changes to the fields inside the instance method will change the implied objects fields. And our call line is object identifier dot method identifier and then the parameter listing. The object identifier is the implied object. Instance methods are written below fields and constructors. So let's look at what would reduce look like in our class. So here's our class fraction. Reduce would sit just below our fields. There's no constructors written yet in here. There's a default constructor, but we haven't actually talked about how to write our own constructors yet. So it would just go right below our fields. So this is a two-step process to reduce a fraction. We're going to find the greatest common factor, and then we're going to divide both the numerator and the denominator by this greatest common factor. Notice nothing is returned here, but the fraction that invokes this method will be changed when it's done. So when this is done, if G has invoked reduce, G will be changed even though nothing is returned. Include this in front of a field is valid but is not needed. So when we talk about the implied objects field, we can say this.num, this.denominator. People often don't do this. So what this would actually look like is people would write it like this. Okay? A couple things to note. Any method associated with a class must be placed below all fields and constructors. There are no custom constructors in this case, so we're fine. Again, constructors are special methods used when an object is first created, and the presentation on constructors will explore this further. Instance method, no static in the method header. This will modify the implied objects field. The implied object is the object used to invoke reduce. No need to return a value in this case. So my question here is, how many instance methods are there? To the left is a version of the fraction class with 3 instance methods, and we can see those there. There's 1 instance method, 2 instance method, 3 instance methods. Pardon me, that was my dryer. Due to space restrictions, none of the methods have proper headers. Don't forget yours. There should be a proper header explaining each of these methods. We know these are instance methods because they do not have the static modifier in them. There's no static modifier, notice. And you can include as many instance methods as required. So here's another example of an instance method. This one will find larger. So here's my method header. This method takes a fraction object as a parameter. It will return a reference to the larger fraction between the implied and passed fraction object. So here's our parameter, fraction, other, and our return type, fraction. If I'm passing a single object into an instance method, I like to often call it other because the implied object is called this. So essentially I calculate the decimal representation of each fraction and then to figure out which one's larger. Let's look at a couple things. Remember, there are 2 fraction objects here, the passed object and the implied object. I don't need to pass two fraction objects to figure out which one's larger. I just need to pass one fraction object because this is invoked with an implied object. So that if I want to return the past object or a reference to the past object, I use the term other because that's what I've named the parameter. But the question is, how do I return a reference to the implied object? Well, this is where I use the reserved word this. So to return a reference to an object, write the variable name. To return a reference to the implied object, use the reserved word this. Again, watch this. Multiplying num divided by denom by 1.0 is required to convert the value to a double for comparison. Otherwise, you'll get the logic error here. And to access the field of a past object, we use the name in front of it. So my past object here is other, and I'm going to say other.num to access that, other.denom to access the other one. So this is a really important slide because it really highlights that point that even though I'm only passing one object, there are two objects here that are at play. We often think about our implied object and our past object. So let's talk really quickly about some benefits of objects. Some of these will become more clear in later presentations, but objects provide modularity, so the source code of an object can be written and maintained independently of the source code for other objects. Once created, an object can be easily passed around inside the system. Information hiding is not going to be as clear yet because we haven't talked about encapsulation, but I put it in here anyways because some people have seen this and I'm starting to get questions about it. So by interacting only with an object's methods, the details of its internal implementations remain hidden from the outside world. This is called encapsulation. We're going to explore this in a later presentation. This is a big one, code reuse. If an object already exists, perhaps written by another software developer, you can use that object in your program. This allows specialists to implement, test, debug complex, task-specific objects, which you can then trust to run in your own code. Java uses thousands of classes that have been written by someone else. Pluggability and debugging easy. If a particular object turns out to be problematic, you can simply remove it from the application and plug in a different object as a replacement. This is analogous to fixing mechanical problems in the real world. If a bolt breaks, you replace it, not the entire machine. Think of video games now. There's a really popular video game out there called Warframe, and it's interesting because, you know, every time you start it up, what happens is it goes and checks for an update. What it does is if something needs to be changed, it doesn't download the entire game again. It downloads one specific component, and it plugs that in because maybe they've updated that component. Same thing with Minecraft. When you're playing Minecraft in the latest update, they have sheep, I believe, that now produce meat. When you get that update, it doesn't download the whole game again. It just downloads the class that defines the sheep and any other classes that are related to it in this sense. So these are four really important ideas I want you to know. Information hiding, it's okay at this point not to be too clear on that because we'll explain that further in our next presentation. Any questions? As always, whether you're in my class or not, if you have questions or comments, please post a comment on my YouTube channel. Have a great day.